Okay, hi everyone, welcome back to this live stream from Windows Server 2003. So I just want to share my screen. Okay, so Microsoft exam objectives covered in this chapter: manage remote access, manage packet filters, manage routing and remote access routing interfaces, manage routing protocols, manage TCP IP routing, manage routing protocols, manage routing tables, manage routing ports, implement secure access between private networks, troubleshoot routing and remote access routing, troubleshoot demand dial routing, troubleshoot router to router VPNs. So, as of the use of IP networking has grown, so has the demand for easy to install and easy to configure routers. Not every small business that wants to connect to the internet or connect to remote offices can afford an expensive router and a certified professional to administer it. Microsoft's first attempt to solve this problem was the version of the Routing and Remote Access Service RRAS included in the Windows NT 4.0 option pack, which is the direct ancestor of the RRAS components included in Windows Server 03. The Windows Server 2003 version of RRAS is a fully functional multi-protocol router. It can handle routing, Internet Protocol IP, Inter-Network Packet Exchange IPX, and AppleTalk traffic, and it can be extended by third parties to add additional network protocols or routing methods. The idea behind using RRAS for routing is that you can just enable RRAS on a Windows Server 2003 machine and use it as a router in addition to whatever else you have it doing. For example, you could use a Windows Server 2003 computer with RRAS for routing, IIS for Simple Mail Transfer Protocol SMTP mail and web service, and two network interface cards NIC to serve as a combination firewall, router, and internet server. So understanding IP routing. Routing is the process of delivering traffic to the correct destination. IP routing is simple to understand at the most basic level. Packets have addresses, and the process of routing involves getting a packet from its source to the destination. The mechanics of how that happens are a little more complicated, though in the following sections we will see exactly what routing does, how routing works, and how Windows Server 2003 handles routing. What routing does. An internetwork is just a network of networks. A simple internetwork might contain 5 distinct networks: Atlanta, Boston, Orlando, Portland, and San Diego. The internetwork is a collection of all these networks, any of which could ordinarily stand alone. Don't confuse an internetwork with the internet. The internet, we all use it. Actually, it's just a really large, really complex internetwork. Complex internetworks like the internet support and even require routing. Consider what happens when you try to send a file over the internet. Suppose you're on the East Coast and the destination is in California. If you look at the map of the physical topology of the internet, you'll see there are a large number of potential routes to get from here to there. Some may be better than others. For instance, one route would carry packets east across the Atlantic, through Europe and across Russia, and the Pacific Ocean to the west coast of the US. That's a legal route, but it would be inefficient. Routing combines the idea that each packet on a network has a source and destination with the idea of associating routes with costs. Routing systems allow administrators to attach a metric or a cost to each leg of a route. In a bit, you'll see how routing systems use this metric information to calculate the most efficient route for packets to take. How routing works. The basic underlying idea in the routing process is that each packet on a network has a source address and a destination address, which means that any device that receives the packet can inspect its header to determine where it came from and where it's going. If such a device also has some information about the network's design and implementation, like how long it takes packets to travel over a particular link, it it can intelligently change the routing to minimize the total cost. So figure 9.1 shows an imaginary network made up of 6 interconnected local networks. These networks, named A through F, are connected by links of varying speeds and costs. This accurately mirrors what happens in the real world, where it's common for internal networks or internet providers to have multiple ways to establish a link between 2 points. So imagine that a client on network B wants to send traffic to a machine on network E. The most obvious route would probably be B to F to E, but you could also use B to C to D to E. Notice that BFE has a total cost of 12, while the seemingly longer BCDE actually has a lower cost of 8. That doesn't appear to make sense because the latter route has a longer path. When you consider what cost really means, though, you'll understand why it makes sense. Assigning link costs is entirely up to you. Normally, you assign costs that reflect your preference for how you want traffic to flow. An expensive or slow link would probably deserve a higher cost than a cheaper or faster link. If you assign a high cost to your most financially expensive links, for example, to meter ISDN connections, they would not be used if there were more efficient links available. Now revisit figure 9.1, the assumption that each circle is really a router. After all, you can hide all the complexity of the network behind a router because only the router is in charge of moving packets. Call your client machine X and your server Y. When X wants to send traffic to Y, it already knows the destination IP address of its target. X will build a packet including its IP address as the source and Y address as the destination. X will then use its default gateway setting to send that packet to router B. Router B receives the packet and has both source and destination address information. By examining the IP address, it can determine that it doesn't know a direct route to the network where Y is located. However, there are 2 intermediate nodes that claim to know how to reach Y, C, and F. Because C has the lowest link cost, the router at B will send the packet to C in a simple routing algorithm. When C receives it, it will go through the same process, forwarding the packet onto D and so on. Eventually, the packet arrives at its destination. Let's take a look at some specific ways in which RRAX actually performs the steps in the preceding example. Routing tables. A routing table is a database that stores route information. Think of it as like a roadmap for the internetwork. The routing table lists which routes exist between networks. So the router or host can look up the necessary information encounters a packet bound for a foreign network. Each entry in the routing table contains 4 pieces of information: the network address of the remote host or network, the forwarding address to which traffic for the remote network should be sent, the network interface that should be used to send the packet to the forwarding address, a cost or metric that indicates what relative priority should be assigned to the route. For example, you could write the San Diego Atlanta route as 10.1.1.0 colon 10, 10.1.254 colon ATL colon 1. Assuming that the interface name is ATL and you want to use a metric of 1. The actual format of how these entries are stored isn't important. In fact, it's not visible in RRAS. What's important for you to know is that every routing table entry contains that information. Routing tables actually can contain these 3 different kinds of routes. Network routes provide a route to an entire network. For example, the San Diego to Atlanta route is a network route because it can be used to route traffic from any host in San Diego to any host in Atlanta. Host routes provide a route to a single system. Think of them as shortcuts. They provide a slightly more efficient way for a router to know how to get traffic to a remote machine, so they're normally used when you want to direct traffic to remote networks through a particular machine. Default routes are where packets go when there's no explicit route for them. This is similar to the default gateway you're used to configuring for TCP IP clients. Anytime a router encounters a packet bound for some remote network, it'll first search the routing table. If it can't find the network or host, it will use the default route instead. This saves you from having to configure a network or host route for every network you might even want to talk to. Static routing. Static routing provides predefined routes in a static routing table. Static routing systems don't make any attempt to discover other routers or systems on their network. Instead, you manually tell the routing engine how to get data to other networks. Specifically, you tell it what other networks are reachable from your network by specifying the network address, subnet masks, and a metric for each network. This information goes into the system's routing table. When an outgoing packet arrives at the routing engine, the engine can examine the routing table to select the lowest cost route to the destination. If there's no explicit entry in the routing table for that network, the packet goes to the default gateway, which is then entrusted with getting the packet to where it needs to go. Static routing is faster and more efficient than dynamic routing. Static routing works well when your network doesn't change much. You can identify the remote networks to which you want to route and then add static routes to them to reflect the costs and topology of your network. In Windows Server 2003, you maintain static routes with the route command, which allows you to either see the contents of the routing table or modify it by adding and removing static routes to individual networks. Dynamic routing. Unlike static routing, dynamic routing doesn't depend on your adding fixed, unchangeable routes to remote networks. Instead, a dynamic routing engine can discover its surroundings by finding and communicating with other nearby routers in an internetwork. This process, usually called router discovery, enables a newly added or rebooted router to configure itself. This is highly equivalent to the process that happens when you move into a new neighborhood. Within a short time of your arrival, you'll probably meet most of the people who live nearby, either because they come to you or because you go to them. At that point, you have useful information about the surrounding environment that could only come from people who were already there. The 2 dynamic routing protocols in Windows Server 2003 are the Routing Information Protocol, RIP, and the Open Shortest Path First, OSPF protocol. Each has its advantages and disadvantages, but they share some common features and functionality. Each router, whether a hardware device, a Windows Server 2003 machine, or whatever, is connected to at least 2 separate physical networks. When the router starts, the only information it has is drawn from its internal routing table. Normally, that means it knows all about the attached networks, plus whatever static routes have been previously defined. The router then receives configuration information that tells it about the state and topology of the network. As time goes on, the network's physical topology can change. For example, take a look at the network in figure 9.2. If network G suddenly lost its connection, the routers in sites A, D, and E would need to readjust their routing tables because they could no longer route traffic directly to G. The process by which this adjustment happens is what makes routing dynamic, and it's also the largest area of difference between the two dynamic routing protocols for IP. So you can see here figure 9.2, a more complex dynamically routed network. The Routing Information Protocol, RIP. The Routing Information Protocol, RIP, is simple and easy to configure, but it has performance limitations that restrict its usefulness on medium to large networks. RIP routers begin with a basically empty routing table, but they immediately begin sending out announcements that they now will reach the network to which they're connected. These announcements may be broadcast or multicast. Routers on other networks that hear these announcements can add these routes to their own routing tables. The process works both ways. Of course, your router will hear announcements from other routers and add those routes to its list of places it knows how to reach. Unfortunately, RIP only supports a maximum of 15 hop counts, the number of routers that a packet can pass through. Microsoft's RIP implementation in Windows Server 2003 supports RIP v1 and RIP v2. The primary difference between the two versions is the manner in which updates are sent. RIP v1 uses broadcasts every 30 seconds and RIP v2 uses multicasts only when routes change. RIP v2 also supports simple, e.g. plain text username / password authentication, which is handy to prevent unwanted changes from cluttering your routing tables. RIP v2 routers also add the ability to receive triggered updates when you know that your network topology is changing, perhaps because you've added connectivity to another network. You can send out a trigger that contains information about the changes. This trigger forces all the RIP routers you own to assimilate the changes immediately. Triggered updates are also used because routers that detect a link or router failure can update their routing tables and announce the change, making their neighbors aware of it sooner rather than later. You can use the RRAS snap-in to set up two kinds of filters that screen out some types of RIP updates. Route filters allow you to pick and choose the networks that you want to admit knowing about and for which you want to accept announcements. Peer filters give you control over which neighboring routers your router will listen to. RIP also incorporates features that attempt to prevent route loops. In figure 9.2, the network topology has the potential to cause a route loop. For instance, say that someone in E wants to send a packet to a machine in A, but G to A and D to C links are down. E sends packets to G, which recognizes that it can't reach A. G also knows that the route DCBA will work, so it sends a packet to D. When the packet reaches D, D knows it can't talk to C, so it sends the packet to E because EGA is normally a valid route. Thus, you can see that the packet will never reach its destination and will loop continuously. This might seem like a contrived example, but in real life, where inter-network links are often concentrated among a small number of physical links, it's a real problem. RIP offers several methods for resolving and preventing loops, including the split horizon and the poison reverse algorithms. Despite their cool names, it's not important to understand how they work to pass the exam. It's enough to know what they're for and that RIP implements them to protect against routing loops. RIP has two operation modes. In periodic update mode, the RIP router sends out its list of known routes at periodic intervals, which you define. The router marks any routes it learns from other routers as RIP routes, which means they remain active only while the router is running. If the router has stopped, the routes vanish. This mode is the default for RIP on LAN interfaces, but it's not suitable for demand dial connections because you don't want your router bringing up a connection just to announce its presence. The auto static update mode, the RRAS router broadcasts the contents of its routing table only when a remote router asks for it. Better still, the routes that the RRAS router learns from its RIP neighbors are marked as static routes in the routing table, and they persist until you manually delete them, even if the router is stopped and restarted or if RIP is disabled for that interface. Auto static mode is the default for demand dial interfaces. The open shortest path OSPF protocol. RIP is designed for fairly small networks. As it turns out, it can handle only 15 router to router hops. If you have a network that spans more than 16 routers at any point, RIP won't be able to cache routes for it. Some parts of the network will appear to be, or in fact will be, unreachable. The open shortest path first OSPF protocol is designed for use on large or very large networks. It's much more efficient than RIP, but it also requires more knowledge and experience to set up and administer. RIP routers continually exchange routing data with one another, which allows incorrect route entries to propagate. Instead of exchanging routing data, each OSPF router maintains a map of the state of the internetwork. This map, called a link state map, provides a continually updated reference to the state of each internetwork link. Neighboring routers group into an adjacency. Think neighborhood within an adjacency. Routers synchronize any changes to the link state map when the network topology changes. Whichever router notices its first floods the internetwork with change notifications. Each router that receives the notification updates its copy of the link map and then recalculates its internal routing table. The shortest path first in OSPF refers to the algorithm that OSPF systems use to calculate routes. Routers are calculated so that the shortest path, the one with the lowest cost, is used first. SPF calculates routes are always free of loops, which is another nice advantage over RIP. OSPF networks are broken down into areas. An area is a collection of interconnected networks. Think of an area as a subsection of an internetwork. Areas are interconnected by backbones. Each OSPF router keeps a link state database only for the areas it's connected to. Special OSPF routers called area border routers interlink. Figure 9.3 shows how this looks. So you can see here figure 9.3, a simple OSPF network. Area 1, area border routers, backbone, and area 2. Microsoft's OSPF implementation supports but doesn't require the use of route filters, so any Windows Server 2003 OSPF router can choose to accept routing information either from other OSPF routers or from other types of routers, e.g. those using RIP. In addition, a desirable feature not always found in OSPF routers is that you can change any of the OSPF settings discussed later in this chapter and have them take effect immediately without having to stop and restart the router. So I'm going to leave it here today for this live stream for server 03. Thank you for listening and have a nice week.